Okay. So this new unit is called conics. And I'll kind of reiterate this over the next couple of weeks or 3 weeks. But why are these called conic sections? True. More specifically, it's doing something called a double napped cone. If I get a chance to go to Michael's from Arts and Crafts store, I'll try to bring some styrofoam cones and maybe use like a sharp knife, maybe from the hearth downstairs, and cut it. So if you take, this is called a double napped cone. I'm not sure. I know the double part, but why napped? I don't know what that means, but I guess because of the points are going towards each other. It's called a double napped cone. If you're like again, go to Michael's, get the styrofoam cones, get a toothpick and connect it like this. Then cut the cones in a variety of ways. The cross sections will represent the graphs that we're going to be doing in this unit. For example, or I mean, more specifically, a plane, right? If you want to use a geometry term, like what if I took a plane and cut the plane parallel to the circular base? Get a circle. You get a circle, yeah. Yeah, if I took a cone, cut it like that, look at the cross section, I get a circle. Great. What if I cut it at an angle through the body of a cone, mind you? I get an oval. Yeah. Yeah, if I took a plane, cut it at a slant through the body of the cone, I get an oval. Yeah, totally, 100%. Which you call an ellipse. Okay, what if I cut it at a corner? This is a tricky one.
Parabola.
You get a parabola. Yeah, actually, if you were to take up a little chunk here, pull it out, that cross section will form a parabola. Exactly.
Is there a straight line?
Was that? No, that's gonna be a different one. Oh yes, that's what you get. Yes, yes. And then lastly, if I cut both cones, but in such a way that's perpendicular, the plane is perpendicular to both circular bases, you get two things that look like parabolas, but they actually will be what we call a hyperbola. They will look like this. It's like having two parabolas that are going against each other, that are going away from each other. So that's called a hyperbola. So those are things we're going to talk about. So I'm going to kind of start you guys kind of easy. These problems will get more complex, and I can make these incredibly complex. We'll see how deep, because it is good to do complex problems to kind of get you guys thinking more analytically. That's kind of the whole point of this. Okay. And by the way, this was, guys, quiet, please. This was an altitude trig honors concept. When I taught altitude trig honors about a decade ago, we always covered this. Now things have moved around, so now I cover it, which I like because I like this topic. All right. So we're going to talk about circles today and parabolas. So circles are very, very straightforward. First off, let's just plot these 2 points, 6, 7, 11, 7. Well, that's pretty obvious. What's that distance? Great, exactly. Yeah, even my second grade son can do that one. So yeah, that's fine. That's easy, right? Okay, plot the point 9, 11, which will be somewhere over here. No calls B. Again, this is O. This is A. Okay, what do you think OB is going to be?
3, 4, 5.
Yeah, because if you do Pythagorean theorem, 4 up, 3 right. If you do Pythag, you should get 5. Now, do you guys know the distance formula? Kind of looks nasty. Yeah, I mean, if you haven't used it in a while, it's one you can easily forget. But really, if you think about it, it's just a glorified Pythagorean theorem, right? I mean, you're taking the difference of x's, squaring it, difference of y, squaring, adding those squared differences, and then squaring the whole thing, which is getting the hypotenuse, right? So d is a hypotenuse. I personally never really used this formula. If I have to find this between 2 points, I just use Pythagorean theorem, right? Just I just can remember it more easily. But you can use distance formula if you want to be more formulaic about it.
Any situation where you're gonna have to.
No, nope. Well, yes, if like I give you the distance between 2 points and a missing coordinate, I suppose. But you can still use Pythagorean theorem in a way to kind of work it out and find the missing side and find the missing coordinates afterwards. Yeah, the Pythagorean theorem is gonna be your best friend, right? Okay, point C, 10, 4. Hold on. Now I'm off a little bit. Okay. So 10, 4, let's plot that. Same thing, right? Still 5, right? Because you're going 3 down, 4 right. Okay. All good? So, what we noticed is that what is a circle? This is a pretty simple definition. A circle is a set of all points that are equidistant from a fixed point. That fixed point, what do we call that? Good. And the equidistant, that's going to be the radius, right? That's all. That's all it ever is. That's a circle. Sometimes we use a more formal term called, we want to get really fancy, the Euclidean definition. Anyone know who Euclid was? More specifically, father of geometry. Yes, father of geometry. So that's called the Euclidean definition or formal definition, whatever. Now, armed with that knowledge, how can I make an equation in a circle? Well, it's supposed to have equal distance, right? Like again, if I have a center here and I got a bunch of points around it, actually, this came out quite, wow, I actually quite impressed myself. Yeah, it's usually hard to do that perfectly. Okay, not that perfect, but good enough. Okay. So if I think about it, what if I call this x, y? What if I call this h, k? And what I call this r? Okay. How would I make an equation? What do you guys think? If I do Pythagorean theorem, right? Usually my color palette's not this good today, too. I don't know what's up with me today. Anyway, got good color palette. Anyway, so yeah, what's a horizontal leg going to be called? That's the difference in the x coordinates, right? Between the center and the point on the circle. And what would you call this side? So if I do Pythagorean theorem, what do you get? You get a relationship for the circle, which is the equation of the circle. Equals r squared. Yep, that's it. That's all it ever is. Some students who don't really fully understand it, like, oh, I gotta memorize, I can't remember. Like, no, you guys are honor students. You guys could totally, you guys totally got this. That's it. I now quickly derived a relationship that relates all these points on the circle, right? But of course, I have to follow that definition of equal distance to a fixed point. Fixed point being h, k, that's the center, r being the radius. That's all there is. I didn't do it specifically for this problem here, but if I did, it's not that hard. X minus 6 squared plus y minus 7 squared equals 25. Boom, done. Right? For the problem we just scrapped up above with points O, A, B, C. There we go. Okay, does that make sense? That's the foundation of this section. Still gonna go over parabolas too, because I need to talk about that. But let's look at some problems. We good?
Oh, that's all. Oh, no. Okay, that must be.
What's an R? All's good? All right, let's keep trucking. All right. Yeah, we can plot really quickly. -3, 4. Raised to 7, so I got to go 7 away. Oops, sorry. Sorry, that was terrible. I could do better, but you get the point, right? There you go. Your radius is 7. The center is -3, 4. Go try the other ones really fast. Shouldn't be that hard. Right? Here, the center. If you don't see H and K, assume 0, 0, right? 10. What do you think about part D? We gotta do about those 15s. You gotta divide it out, right? So that you match the general form. Yeah, good.
The radius is √5. Yeah, the radius there is √5.
Yeah, it's gonna be. I thought it was gonna be perfect today. Thanks, guys. My apologies. √5 is roughly between what two numbers? 2 and 3. Yeah, my apologies. I knew that seemed a little too big. Okay, for part D, I should divide by 15, right? So what's your race going to be in this case? For part D? 2, right? So that becomes 4, right? And your center is at -1, 2. So I know you guys can graph that, so we'll just move on. I'm not too worried about that. Okay. Here, pretty easy. You don't have to use this formula. How far am I moving to the left to get from the center to a point in the circle? 5, right? How far am I moving down? 6. So it's √61. So it's X. We're good there?
That's what center is.
Oh, sorry. Happens you're on autopilot. You miss things like that. Okay, we're good? Okay, cool. All right. All right, say you have that as your diameter. And by the way, what will happen is that after today, we're going to cover circles and parabolas. I only see you guys one more time this week on Wednesday. We'll cover ellipses, I think, that day. Not sure we'll do hyperbolas, probably just ellipses. We'll do hyperbolas next week. Then we'll start putting all these together. And then I'll start showing us more advanced problems and then word problems with this stuff too. So this stuff will get more advanced over the coming weeks. So it's going to seem easy right now. Trust me, we'll get a little more challenging. All right. What's halfway between those 2 points? What's the midpoint of that? What do you guys think? Midpoint? Go ahead, Allison. -1. Negative 1 for the x, and how for the y? Yeah, negative 1, right? All you're doing is you're averaging the x and y coordinates of the endpoints, right? So that's pretty easy. So it looks like I have to go 4 right, 3 up. So what's my radius here? Yeah, I've kept them pretty simple so far. Write the equation. Yeah, that's easy. Okay, I'm not gonna make a mistake this time. So it's gonna look kind of like this. If I go 5 up, 5 down. Okay, so that's kind of a crappy circle. Okay, for part D, but you guys are with me so far. We're good? Cool. All right. So part D, what does it mean to be tangent to a circle? Like we're going off on a tangent, going off in the yonder, right? That's all. Just a point that grazes the graph. So 3, 2. How would I find that equation? What would I do? Kieran, you good? Yeah, we got. Right, which is a negative reciprocal, right? Yes, of course. Right. Strongly suggest you guys use point slope form. In fact, actually get in the habit of using point slope form. Especially as we move on to calculus, you'll be doing tangent lines like crazy. Tangent lines are kind of like a big deal in the first semester of calculus. It's actually the derivative, the slope of the tangent line to a curve is called a derivative, which we'll talk about when the time's right. But you just want to get how to do that because we rarely use y equals mx plus b. If you want to rearrange into y equals mx plus b, go ahead. But just better to kind of use this x1, y1 is a point given, and the slope of your line. Well, what's the slope of the radius? That was up 3/4. So what's that blue line? Negative 4/3, exactly. Right. So that slope is negative 4/3. I'll call it MT for slope of the tangent. So negative 4/3, x minus 3, y minus 2. Okay. Okay. Want to get to what?
Oh, it's just.
Yeah. So a little bit of geometry going on here. You guys should have done geo honors or if you did geometry in middle school. Okay. Let's look at 5. Okay. That should be pretty simple. Just 3, 4, 3, negative 4. Thanks. Okay, good. I think I got it right now. Doing 6. And then kind of hard to tell where it's touching it, but you can just put 6 in for x, right? And work it out. I mean, I think I kind of know where it's touching it, but wouldn't that be 9 plus y plus 4 squared So it'd be 0, -8, I think. Is that right? Yeah, my graph was way off then. Yeah, it was really off. So, oh well. Actually, this one seems about right. That one seems off. So, yeah. So, find the coordinates of the points where they intersect. 6, 0, 6, -8. Okay. Again, pretty straightforward stuff. Oh yeah. Okay. Now it gets a little juicy, but trust me, to get even juicier beyond this one. You'll see some of the problems. I can't wait till we do this. It's gonna be fun. I think I'm making mistakes. So I think just bored with these problems. So anyway, for number 6, completing the square. How are you guys with completing the square? You guys okay? Yeah, I haven't talked about you guys. So I'm gonna go back to Mr. Ban if you guys are bad at it now. Really simple. It's not that hard. You take half. No, you're not gonna suck. You're gonna be great at it. Actually, it does get complicated with ellipsis and hyperbolas. I know. No, I got brace you guys. All right, here we go. You already said that? Okay, all right. Okay. You probably said with a smile. All right. Anyway, really? No, this is a pretty nice guy. Get to know. Really? Oh. Okay. Okay, guys. Really, guys, back in, guys. We got parabolas to do, so let's get back. Okay, really simple, guys. Quiet. All you're trying to do is write this as something squared, right? That's the whole intention of this. So what you need to do is figure out how to turn x squared plus 2x into a perfect square trinomial. Tri meaning 3 terms, perfect square meaning the first and last terms be perfect squares. X squared, of course, is a perfect square, right? Square of x squares x. Now, because the middle term is 2x, here's a trick. You take half of 2 and square it, which is 1. Great, excellent. So you put plus 1. A2, do the same thing. What's half -4? And then squared. 4, great. So you put plus 4. And whatever you add to the left side, you must add to the right side, right? For balance. So you get 57, I think. And that's x plus 1 squared, y minus 2 squared. And that's how you can write the equation of circle in a standard way. Because now I can easily identify the center, which is -1,2, raised to 57. Done. That's called completing the square. Now, for those who are doing the PSAT this Wednesday, this is a question sometimes asked. Actually, I wouldn't be surprised if you saw a question like this. Desmos is built in to the SAT. You can just type that in and look at the center and count to find the radius. You could do that because they'll probably say, oh, what's the radius of this? Or what's the center of this? Or whatever. But to do it by hand, you should know that as well. So, but I wouldn't be surprised if you saw some of the PSAT this Wednesday, question like that. I completed the square. Completing the square means you take half of the linear coefficient.
Half of the.
Linear coefficient.
Okay.
And then take half and square it. Half of 2 is 1. 1 squares 1.
We just add that.
Exactly.
As a.
Because because this becomes this now, right?
Number.
Right, because now I can factor it.
Oh, it's because if you have. Okay.
Right.
Okay.
So I can factor it.
Yeah.
Right? Okay. Let's keep moving, guys.
I see.
But how would they know?
It's like on college board.
No, but you get to choose what scores to send, though. No?
Some schools give like every single.
No, but your college board score, but you but on the on your college board score report, they wouldn't show that you could choose you could hide certain tests if you wanted to. But how would they know? Okay. All right. Jeez. Screw Georgetown. That's crazy. No, Georgetown's a good school, later on. Okay. All right, guys, let's move on to parabolas. Guys, quiet, please. Thank you. All right, let me give you guys a definition of parabola. Now, guys, Thomas, thanks. All right. Now, I know you guys done parabolas many times. You've done quadratic functions. You probably haven't seen it defined in this way. A parabola is a set of all points equidistant from a fixed point and a fixed line. The fixed point we call the focus. Fixed line we call the directrix. Kind of a funny name. Okay, that's the Euclidean definition of a parabola. Can't spell. And I'll show you the derivation. It's a little bit of a funny derivation. It is a cross-section of a cone that was parallel to the side of a cone. We talked about that, right? When you have the cone here, and you slice it that way, you know, something like you get a parabola cross-section, more of a corner, but and every point of the parabola is equidistant to a point called the focus and a line called the directrix. They're actually I just repeated a second bullet point, but I felt like typing it anyway. So let's say your focus is at 0, 2. We'll say your directrix is over here. Now the directrix, I tend to use a dashed or dotted line for the directrix. It looks like an asymptote. It's not. There's not asymptotic behavior. But the bottom line is this. You need to be equidistant from these. So you need to be of equal distance from this point and that line. One point should be pretty obvious. What point is going to be
0, 0.
0, 0 for sure. 0, 0 is 2 away from each. That's very obvious. The other points are not as obvious, but it's going to roughly look something kind of like this. Kind of like a bowl or dish shape, right? So for example, if I pick like a random point here, say I call it x comma y, and say I call this d1, and say I call this, geez, that should be straight down, d2. d1 is going to equal d2, just so you know. That'll always be true. d1 is the distance from the focus to a point on the curve. d2 is the distance from the point of the curve to the directrix. The distance from your point of line is going to be a straight shot where that segment is perpendicular to that one. I mean, it's pretty obvious the vertex 0, 0. The axis of symmetry is pretty obvious. It's x equals 0. The graph, like I did a rough sketch, right? A very rough sketch. How do you know exactly what it's going to be? I'm going to show you in just a moment. How do you know exactly how this graph's going to look like and what the equation will be? I'll get there. One other thing I need to add to the diagram too, which is going to really kind of make things a little messy. This is I'm going to call P. P is defined as a distance between focus and vertex, or vertex and directrix. Okay, that's what P is. What does that mean to?
Yeah.
So P is gonna be 2. And by the way, P is positive if you opens up or right. Yes, our parabolas can be sideways. We can have sideways parabolas. Or P would be negative if it opens down or left. Yeah, go ahead.
I'm sorry, are there just infinite D1 and D2s?
Oh, of course. Yeah, 100%. Yeah,
Okay.
of course. I just pick a hypothetical point. Yeah, 100%. Right. No, I could have a point like way over here.
Yeah.
And then just from the focus that and here from here will also be the same.
Okay.
Yeah. Because that's gonna kind of dictate the width of this parabola, that p value. So yes, it's getting a little more complex now, but it's not that hard once you have it all kind of straightened out. One thing I do want to show you guys really quickly before I finish off the problem. Actually, let me finish off the problem. Then I'll show you guys the answer. So we had this, right? Let me just copy it one more time. We have something like this here. So write the equation. So generally the equation is going to be this: y equals. Let me think about this one here. Make sure I got this right. Actually, let me show you the derivation. Derivation is going to be better. Give me a moment here. And you guys are not going to derive it. I'm just going to show it to you and walk you guys through it to make you understand why the equation works the way it does. Okay. So derivation of a standard equation of a parabola with vertex of 0, 0, and vertical axis which is opening up. Okay. So if you think about it, that's focus, that's right what you're talking about, right? That's a random point on the parabola. That's D1, D2, will have to be the same. We're cool with that so far? So D1, if I use distance formula, in this case, I kind of am using the formal definition of the distance formula, which is going to be x squared plus y minus b squared. Because if you think about it, the distance between that has an x value of 0, so that's going to be x, that distance. And that's a y by a piece of y minus b is that distance, or that difference, say that. Then if you do it between the directrix, they share the same x coordinate, so that's going to be 0, that's y minus p squared. Sorry, y minus negative p squared. You guys see why it's x comma negative p on the directrix? Because that's going p down from the vertex, so that's x equals, sorry, it's y equals negative p. So that's going to be x comma negative p at that point. Hope that makes sense. So y minus negative p is y plus p. That's 0 comma p, that's p away, that's going up. So if that makes sense, we're okay with that. If you ever set these equal to each other, d1 equals d2, and you have to square both sides to get a little radical. What's going to happen is a lot of terms drop out. It's actually a pretty cool derivation. And the derivation becomes this. So if you're ever curious why quadratic functions take on that shape, it's not because, okay, well, here's the point spawn just happens. No, this is the reason why. We still teach in algebra 1 because you guys aren't quite ready for that. It's too abstract. But this is the real reason why parabolas are the way they are and why they're tied to quadratic functions because of this. Now, if you want to do the horizontal axis symmetry, just kind of reverse it. Just have it point to the right and kind of mix that, switch x and y coordinates. But ultimately, if you square both sides and FOIL and do all this like fun stuff and cancel stuff out, you want to be x equals 4py, where p is the distance from the vertex of the focus. So coming back to the notes again, I'm just going to say it's x squared equals 8y, or y equals 1/8 x squared. So the formula goes like this: x squared equals 4py. Sometimes I write like this too, just so you know. As a transformation. That's okay, by the way. Sorry about that. Supposed to be okay. As a transformation, we can write like that. And think of this as A if you want. I don't know if you want to do that. You can as a vertical stretch. But it's a little funky. Some people write like this, by the way. You might see some textbooks say y equals 1/4p x minus h squared. You might see some, if you look online, you might see that also. That's just basically a manipulation of this, right? They're the same thing. I prefer to write it this way because I'm going to kind of do that for all the other shapes we'll do in this unit, for ellipses and hyperbolas. So I kind of prefer to write that like that. Okay, questions? All right, let's keep moving. So over here, the focus at -2, 0, directrix x equals 2. So what direction do you think this is going to open? Yeah, scope it to the left. Yeah, exactly, 100%. Exactly. So in this case, your vertex is still 0, 0. Axis symmetry is y equals 0. Now the equation is going to look like this. It's going to be y squared equals 4px, just so you know. And that just comes from the derivation if you work it out. So y squared will equal negative 8x. So when x is not squared, it opens horizontally. When y is not squared, it opens vertically. Like y equals x squared, we were so used to that, right? If x equals y squared, that's going to be horizontal. And it's going to the left, so you make it negative. And again, it's not a terribly accurate sketch, but if I plug in -2, I should get 4 for y, which actually I was pretty good. Actually, that does look like it's happening. You have points at -2. Yeah, that actually makes sense. -2, comma 4, and -2, comma -4. Because if you think about it, what's that distance? 4. What's that distance? Look at that. Kind of got lucky there. Yeah, that makes sense. I mean, once you understand what's going on with this stuff, I don't want you being haphazard with your graphs. I do want your graphs to look accurate. I don't want just sketching something kind of like, sloppy way. So, we want to make sure that we're being accurate with our graphs. Okay, questions? Nope. All right, let's keep going. Okay, so in general, what's happening? P is a distance from the vertex to the focus. Also from the vertex to the directrix. Orientation, up/down, or right/left. X squared equals 4py. Or y squared equals 4px. Focus will be 0, comma p. Directrix will be x equals p here, y equals p. Sorry, my bad. I mixed it up. My apologies. Axis symmetry, this will be x equals 0, y equals 0. And remember, p positive, p positive, p negative, p negative. Oh, actually, the directrix might. Oh, sorry, hold on a sec. My apologies. I kind of messed up here. That's supposed to be negative p. Was that your question? Oh, okay. Sorry, my bad. And the other one should be p comma 0.
Yeah, that was.
Yeah, my apologies. My apologies. My bad. We got that straight. Sorry. 0, comma p, p comma 0. And the director is supposed to be y equals negative p or x equals negative p. And p is negative, it just reverses. Okay, so we're cool with that. All right. So I'm not sure how far we can get with this, but we're not gonna but the homework that I'm assigning you guys is gonna keep the vertex at 0, 0. I believe so. Yeah, the homework, I have the homework right here. I'm gonna hand it out in just a moment. I think everything's gonna be at 0, 0. There is one word problem, which is pretty good. And actually, it's snuck into notes. So I'm actually not going to do number 6 because I want to see how you guys do. 5, we could do that next week. It's not next week. Sorry. Well, maybe next week, or I could talk about on Wednesday. And 7 I could talk about later. Yeah, let's just do these two graphs really fast and just wrap up the notes. So 0, 0, directrix 3/2. So here's 0, 0. Y equals 3 halves. So I expect my graph to be like this. X squared equals 4 times negative 3 halves y. So if I plug in negative 6 for y, x should be 6 or negative 6. 1, 2, 3, 4, 5, 6. 3, 4. Your folks to be like right here. So hope that makes sense. How's that figure that one out?
Can we like leave it as x squared equals negative 6?
Yeah, totally 100%. Yeah,
Okay.
exactly. I'm fine with that. Yeah, and actually, in this interest of time, I won't do the last example. So let me pass up homework. Homework will be 9.2 and 9.3. I'll put in school as well. I'll put and Dave, I'll put the soft copies.
Okay, thank you. Yeah. B period and then. Yeah, after B period, it's grades from 10:35 to 10:50, and then C at 10:55. So. I'm just. No IR.
Yeah, I have Jacobs right now. We missed it. Not gonna be here this Wednesday.
I'll see you guys later.
Thank you.
It's a Thursday we got out like, oh.
Watching
Lunch is at the end of the day.